as a case. Uh-oh. Oh, what just happened to the projector? Trying to find out which audio channel is being used for. Okay.
There were two things. That's the one. That's the best one.
Okay, so it's using the right channel for recording. All right. Let me see what, we still got about 3 more minutes. Or I can hear the wind from here.
That's usually like the same.
Sorry?
That's easily like 80 miles an hour.
I don't think it's quite 80, but I think it probably is upwards of 30 or 40.
Feels like it was not raining.
Hmm? Yeah, it's starting to rain just a little bit. All right, I'm just setting up all the. Yeah.
Actually, it was actually windy.
Well, that's one good thing about being shorter. The lower center of gravity.
It's only like
Well, the semester before, well, so the spring semester before the pandemic, I was riding my bicycle to work. And I actually took off at about 10 o'clock. So one day during the storm, I was riding my bicycle home in the storm. And it was okay. I was actually kind of dry because of the poncho, but I almost got blew, into a ditch, on the bike lane.
Scary.
Cars was not an issue. There were no one was driving on the road. Just this crazy cyclist trying to get home. I was in no danger of getting hit by a car.
Just tree branch.
Tree branch or meteor falling into the ditch because of the wind. Yeah. Well, we got quite a few people who are out sick because of, I guess, the weather or something. Spring break fever. Yes. Maybe. All right, so it is almost 5:30. We're getting there. I'm just looking at the clock. Yep, it is 5:30 now. All right, so what we'll do today is, first of all, I finished grading exam 1 over the break. In fact, it took me a long time. I think the average of exams I could grade per hour was 3. And this is a class of 50 plus students. So you guys can do the math, okay? Some exams were easier to grade because there were missing answers, but on the average it was there somewhere between 15 minutes to 20 minutes per exam. So I did go through, even for the first few questions, I did go through all the rationale of how people derive the values and so on. At least I try my best. So there's that. So the score that you see is pre-scale, okay? In other words, that's the raw score. With the highest score of the class was a 3.96 something. The 5th person or the 5th highest score is a 3.85. So I'm gonna scale that to 4.0 and everybody else would just get the same linear scaling factor. So whatever you score you see, it'll be that score times 4 divided by 3.85, and that would be your score for exam 1.
Can you say that again?
Hmm?
Can you say that again?
It's getting recorded.
Oh, okay.
4 divided by 3.85, that's your scaling factor. Yep. All right. So what we'll do today is we are continuing to talk about D-flip-flops and other basic memory devices. In fact, we are close to getting this part done. Let me maximize the screen because right now it doesn't seem maximized to me. So let me maximize it. There we go. All right. So what we'll do today is we are going to go into the last portion here because this is actually pretty important. So multi-bit as a register it looks like this. So when you look at, let's start with individual items here. So each individual item is a resettable, level sensitive, edge sensitive D flip-flop, okay? So let me let those people in first and then we'll continue with the lecture. But I probably need to tell people, if they want to show up on Zoom, they have to do it before 5:30 because otherwise it's kind of distracting to have to continue to let people in. All right, so right. So when you look at each individual item, it has a clock. So the clock tells us it's edge sensitive. So when the clock line goes from a 0 to 1, or when we have a rising edge, at that moment, okay, things may potentially update. But why do I say may? Because it also has an enable. So the enable is what we call the level sensitive part of a D flip-flop. So the enable has to be a 1, and then the clock has to see a rising edge transition, which means it is going from 0 to 1. And then we also have D, which is the data that this particular D flip-flop needs to remember. And then we have a reset. Useful if you want to change the content back to the default, which is 0. So those are the input pins. Each one has 4 input pins, and each one only has one single output pin, which is Q in this case. So Q is nothing more than just the state of that particular bit. So now the question is, now that we have 8 of these things, how are they interconnected? Yep, go ahead.
Wait, just to confirm, those 8 circuits in there, are they the circuit that's right above it?
Yes.
Okay.
So each one of these circuit here is really just a circuit here. You know, it has a clock, it has an enable, it has a data pin, it has a reset pin, and it also has an output pin of Q. So you can imagine each one of these things is just a sub-circuit that looks like this. And this is where the sub-circuit itself is where we left off right before the break. You guys still vaguely remember? Okay, very good. All right. So now the question is, now that we are stacking 8 of these things, how are they related? So we'll start with the clock pin. This is the actual clock pin of the entire circuit that is made out of these sub-circuits. You can see the clock pin is using a multi-drop topology. What that means is there's only one single clock pin here. There's only one clock node, and it connects to every single clock of all 8 of these D-flipflops. They all share the same clock. Is that okay? So that means in terms of timing, when they update together at the same time. Do we have any questions at this point? Okay. What about the enable? Well, it's the same thing. So when you look at the enable pin of each D-flip-flop, they are all interconnected. So there's only one enable pin, on the outside, and it connects to all 8 of these D-flip-flops. When they're enabled, they're all enabled at the same time. Is that okay? All right. Reset is the same thing. So if you track down reset, which is all the way down here, it is also using a multi-drop topology. So that means, when we assert the reset pin, it will reset all 8 bits at the same time. So there's nothing really special about this circuit other than the data pin. Okay. So the data pin, as an input pin, is the only multi-bit pin. And it's going through a splitter where bit 0 goes to its own D-flip-flop, bit 1 goes to its own D-flip-flop, and then all the way up to bit 7 goes to its own D-flip-flop. In other words, we use one D-flip-flop to remember one bit. But you can look at this entire thing as a 8-bit quote-unquote D-flip-flop, a multi-bit D-flip-flop, which has its own special name. It is called a register. All right, so when you look at the output of each D-flip-flop, the Q of each D-flip-flop, they all go into this merge, which is basically a splitter, except it's turned around. So the D-flip-flop responsible for bit 0 contributes only to bit 0 of the splitter, and so on. So after we merge all 8 bits, they all go to the same output pin, which is an 8-bit output pin that we call Q in general. So are we still doing okay so far? In other words, all you're looking at here is a multi-bit D-flip-flop. That's it. And this is important because this is the smallest and the most important, I would say, data storing device inside a processor. This is not a main memory. This is inside the processor itself. Are we still doing okay so far with this picture? All right. All right, so what we'll do today, and I will give you a preview of today's lab. So in today's lab, I'm going to give you basically quote-unquote self-study time to understand the other components inside the processor. So in addition to registers, we also have multiplexers, demultiplexers, RAM, ROM, and decoder. I mean, those are the basic components. I will go over those components in class 2. Okay, so I'm not only relying on the lab and your self-reading to get through all that material. So I will talk about the general concept, but in the lab, you should probably read the documentation of Logistim as well, because there are specific configurations that you should read in order to answer the questions. But I'll give you a general idea of how those things work.
All right, so let me start up logic sim. In fact, I got one already started, so I'm just gonna use it over here. All right, so we got logic sim. So once again, the most important part is where to find help because you are going to need it during the lab. So you go to help and then you go to library reference and then you will see a window like this. That's okay. And from here, you can look at plexers. We can find multiplexer, demultiplexer, decoder here. If you go to memory library, you'll be able to find register, which is what we just talked about. You can also find RAM as well as ROM. So those are the main components that we are going to need in order to make the processor. What we'll do next today is to look at each one individually, and we will even build some circuits just to test it and see what it does, okay? But I'm not going to read the actual documentation in this class. I'll give you a general idea of how they work, but it is up to the lab, which is another hour and a half-ish, that you can kind of read the documentation and also build your logic sim circuit to test out the circuit, because that's what you'll be doing in today's lab. Do we have any questions before I go into each one to kind of explain what they do and also build some test circuits so that you can get some idea of what they do and how to get it done? No questions? All right. So we're going to start with multiplexers and demultiplexers. Okay, those two are they're very useful. So this is a multiplexer. And when you look at the symbol of a multiplexer, it has multiple input pins. Okay, these are the input pins. It has a select pin here. It has one single output pin over here. It has an optional enable pin over here. So those are basically the interfaces, to a multiplexer. So the question is, so what is a multiplexer? Well, it's basically a railroad switch. That's all it is. In this case, you have multiple rails coming into the switch, and you only have one rail going out of the switch. Is that okay? So the job of a multiplexer is to say, okay, which incoming rail gets to go through the switch to the output of the switch. That's its job. Are we doing okay so far with that general concept of what a multiplexer does? Maybe. Okay, we'll use an example. Okay, so I'm going to use an example here. So let's go to pick up a multiplexer here, and I can just kind of slap it into this circuit. So in this particular one, the default is you only have two inputs, one output, and then each port is a single bit. You can change all of those configurations because, as you can see here, you can change the phasing and also the select location. That's just your cosmetics. But you can also change the number of select bits. One bit allows you to select one of two inputs. If I have two select bits, then how many inputs can I select from? Because with one single input, if the input is a 0, I can choose input 0. If the input is 1, I can choose input 1. If I have two bits for selecting, how many inputs can I select from? 4, that is correct, because input 0, 0, 0, 1, 1, 0, and 1, 1. Those are all binary numbers, but if you want to look at those numbers as decimal numbers, we are looking at input 0, 1, 2, and 3. Okay, so let me extend this, okay? What about 3 input bits? How many inputs can I select from? No? No? 8. It is 2 to the power of the number of select bits. Does that make sense? Because with 3 bits, okay, you go from 0, 0, 0, all the way to 1, 1, 1 as binary numbers. There are 8 of them. Okay, let's do this one more time.
What about 4 input bits, 4 select bits? How many inputs can I select from? It'll be 16 because 2 to the power of 4 is 16. That is correct. Okay. So let's make this
Slightly more interesting. So I'm going to use 2 input bits. Okay, like so. So now you can see how we have input 0, 1, 2, and 3. Okay. And you can also see that this particular port here is now a 2-bit port. Now, how do we know? Well, all it takes is for me to make a mistake, then you can see. So we'll go ahead and attach a input pin, which is 1 single bit, to this thing here. And you can see from the error that, hey, this is a 2-bit port. This pin is only a 1-bit input pin, and that's why it is in orange, because the bit width is not agreeing. Is that okay so far? Okay. So if I were to, if I want this circuit to work, I'm going to have to change this input pin to 2 data bits, like so. Okay, so that fixes the problem. This pin here is the enable pin. The enable pin is not necessary. Okay, it is not required. So you can see once we select the multiplexer, you can also see the other configurations, and you can see how here it has include enable. So that means you can turn it off. So if you turn off enable, then there's no enable pin. If enable pin is turned off, if you disable include enable, that means it is always enabled. Are we doing okay so far with all of those concepts so far? Okay. All right. So now there's one more thing to talk about, which is disabled output. Okay. So disabled output obviously only makes sense when you have an enable pin. Does that make sense to you? Because what disabled output as an attribute controls is what is the output when enable is off. In order to specify it is not enabled, don't you think you need an enable pin? So that means if this is a no, if include enable is a no, then it doesn't matter what you specify as disabled output, because you cannot disable output without that pin. Is that okay? All right. So we're going to make the assumption that yes, we want to have an enable pin here. So now it is a question of, okay, so if the output is quote unquote disabled or not enabled, what is it supposed to do? You got 2 options to choose here. One of these options is very easy to understand. 0, right? 0 is easy to understand. It simply means if the multiplexer is disabled, which means the enable pin is seeing a 0, then the output is just going to be 0s. That's all it's going to do. But the other option, which is floating, requires a little bit of explanation. We talked about floating already when we talked about the controlled buffer. Do you guys still remember the concept of a controlled buffer? We talked about it a long time ago, okay, but it's nonetheless discussed. So we'll go ahead and talk about it again. So what you can kind of think about is to imagine that you have several devices that connect to the same node. In other words, electrically speaking, they're all connected. So if all of them try to talk at the same time, you have a problem. Because, well, first of all, the communication would be garbled because they are all trying to talk at the same time. But from the electrical perspective, they will be fighting each other. Imagine one of these things is trying to specify an output of 1, another thing is trying to specify an output of 0. What do you think is going to happen? It's going to be unknown. It depends on who is stronger. Okay, so the device that is outputting a 1 is trying to source current. The device that is trying to output a 0 is trying to sink current. So you have a source, you have a sink, and there's no actual resistor in between. So that means you have a crowbar, what we call a crowbar in a circuit. You have a short. So the short is going from the device that is outputting a 1 to the device that is trying to output a 0. But nothing is without resistance. There's always resistance.
So in this case, the resistance is inside the transistors themselves. And what do you think is going to happen when you have resistance and then you have current passing through that resistor and a relatively strong current at that too? What do you think is going to happen? It produces heat. Very good. So V squared divided by R is, let me see. Yes, V squared divided by R is the power dissipation at the device that has resistance. Okay. So when this particular heat exceeds a certain point, then the transistor will stop working. So that means you really do not want devices to fight each other, where one device can specify a 1, another device can try to specify a 0. That would not be a good scenario. So that's what floating is for. So floating is basically saying, I am not outputting anything. I'm simply, okay, so think about a line, okay? So just imagine there's a line from where I'm standing here, extending to the wall over there. So I can yank the line down, okay, to try to force the level of the line down, or I can push it, try to elevate the level of the line. Does that make sense? Okay. So you can kind of imagine there's another person who can also kind of pull or push the line, another person who can push or pull the line. So if I'm trying to push the line, the next person trying to pull the line, then we're just fighting each other. The actual state of the line depends on who's pushing or you're pulling stronger. So in that scenario, floating simply means I'm letting go of the line. I'm not doing anything with it. I'm simply not outputting anything. I'm not outputting a 1. I'm not outputting a 0. It is as if I'm not connected to the line. Is that okay? Yep.
Kind of like a mole.
It's
Nothing.
There's no logical equivalence in terms of programming to floating. The best way I can describe floating is it is as if it is not connected. Okay, so if you want to write down, what floating means, you can just write down as if it is not connected. So there's no danger of a fight anymore. If the device is connected to the same node, only up to one of them is outputting something. The rest, if they're all floating, then we don't have a problem. Is that okay? All right. All right, so this is a multiplexer, and I'm just going to finish this circuit here just so that we can play with it a little bit. And we can specify this thing to have multiple bits instead of 1 data bit. We'll specify 3 data bits. Okay, so the number of data bits for the multiplexer does not have to correspond to the number of select bits. The number of select bits is only going to control the number of inputs where we can select one of the inputs to connect to the output, but each input and also the output can also have multiple bits. And that's a separate, completely independent configuration for the multiplexer. All right, so we'll go ahead and make this one also 3 data bit, just so that it can talk to the multiplexer. And then we'll have duplicates of this. Okay, so Control D. Control D. All right, so we'll go ahead and make all the connections here. And then we'll have the output to connect to an output pin, which is also going to be 3-bit wide. Like so. And we'll make this slightly more interesting. Make these bit patterns a little bit different. There we go. So now we can also connect the enable pin. Since I do have the enable pin, I want to connect it to something. So this way I can illustrate the effect of the enable pin. There we go. All right. So the enable pin is now disabled because it is connected to a 0. And I do have the multiplexer specifying floating as the disabled output. And this is what it looks like when something is quote unquote not connected. Is you see basically XXX in this case for the output pin,
because we don't know what it is, okay? No one is yanking one way or another on the line. So the line is just, guess what? It's just floating. It's whatever it is. So I know many of you are thinking, but nothing can actually be unknown, okay? There has to be some kind of a voltage on each conductor, relative to the ground plane of the entire circuit. There has to be a voltage of some kind. So if you're wondering about that, my answer is yes, there is a voltage on the line. The question is, nobody's controlling the voltage, okay? So when you have a trace of line or a trace of copper, a conductor that is not connected to anything, it's basically an antenna, okay? So what do you mean by it's an antenna? Well, it means when you have electromagnetic wave that is around it, it can pick up the electromagnetic wave, and that can induce current if there's anything connected on that wire. So that means if something has an output, quote unquote, output of XXX, the actual voltage of that line would depend on, did you just turn on the microwave? How far is the microwave away from the circuit? There's a lot of things that can affect it. But for the most part, you don't have to care. Because when the output is XXX or when it's not outputting anything, it simply means I don't have a specific thing, a specific value to output. Yes.
Someone just said in the Discord that your screen is showing the Internet Explorer window.
Internet Explorer. That would not be possible because I'm using Linux.
Yeah. Want to check if it's sharing code.
I'm pretty sure it's showing the circuit here.
Sorry, you said Firefox.
Hmm?
You said Firefox.
Okay, that makes more sense. I am looking, okay, I can show you guys since you're in the class. This is what I see from Zoom. And the screen I'm being shared here is the circuit that we are looking at. So I cannot think of a way why it would be opening the Firefox because I'm sharing the entire screen. I'm not sharing a window. I'm sharing the entire screen. Hmm? I mean, does anyone here want to kind of just sign into Zoom to take a quick look? And I'm not using Discord at all. I mean, I'm not using Discord in this semester, so. Yep.
This 2-bit pin, is that called the?
This is the selector. Yes, it selects which one is the input, but right now it is useless because right now the multiplexer is turned off, and I specify when it's off, the output is floating, so that means they're all XXX. So I got something here. So Carter. Okay.
Okay, this looks right to me.
Yeah, that's what I thought because the preview of the screen is.
Well, the person who's having issues just said that refreshing the page was.
Oh,
Okay, thank you. I did not turn on the chat. I just didn't want to be distracted. But I suppose I can turn it on if I. Okay. Okay, so it's probably a glitch on the other end. Okay, all right, so getting back to this discussion here. So that means right now we can play with the option of what disabled output means. Remember the two options? We can be floating, which basically means if it is not connected to the output pin here. And the other option is zeros, right? So we can go ahead and make that change and we can see what it looks like in this case. Okay, so we select a component and then we change the disabled output from floating to 0, and you can see how the output pin is reflecting 0, 0, 0 in this case, because the device is turned off. It is disabled. Well, isn't that the same thing? No, it is not the same thing. Because this means I'm yanking that line down. I'm actually trying to specify a value of 0 to the output pin. As opposed to letting go of the line is like, I'm not trying to specify anything. Is that okay? Yep.
Input and output pins can be any size.
The input and the output pin,
The input and are 3 bits.
mhm,
Can you specify that, or could it be any size?
they have to be the same, and they are both controlled by the data bits here. All right, so now we can play with the select pin, and once we enable it, we can play with the select pin. So we'll turn on this thing here. And now we can say, oh, I want this 101, which is a 5, to be the output. So what do I need to specify as my selector in order for 101 as the input to appear to the output? 10, very good. Okay, so because we are just counting from 0, 0, 0, 1, and then 10 is the third pin from the top. So we change this to 10. And the output becomes the same as input 2, basically. This is input 0, this is input 1, this is input 2. And the funny thing is, once you make that connection, it is not a memory device. A multiplexer has nothing, it has no memory capacity, because as soon as you change the input, it changes the output. It is simply a switch. That's all it is. Which input connects to the output? That's the basic function of a multiplexer. Are we doing okay so far with the multiplexer? So do you think I need to explain what is a demultiplexer? What do you think a demultiplexer is, now that you know what a multiplexer is? No. What do you think the DE is going to do to the name?
Specify input paths.
It's basically the reverse, okay? It's the reverse of a multiplexer. So what it means is with a multiplexer, you have one input and multiple outputs. That's all it is, okay? But I'm just gonna show you that circuit too. So we'll go pick out a demultiplexer. Even the shape looks exactly like the opposite of a multiplexer, okay? So in this case, I can also make the number of select bits a 2. So it has one single input pin, 4 output pins in this case. It also has basically the same option. The 3-state I'm not going to talk about in this class. Okay, so so we always keep the 3-state as a no in this case. So don't worry about the 3-state property. But other than that, it also has disabled output. It also can select between floating and 0. And you can also specify whether there is an enable pin or not. The enable pin is the other pin other than the one under the gray dot. The gray dot is always telling you which one is the select pin. So we do okay so far, identifying which pin is which pin. Okay. So in this case, the only real difference is the direction. With a multiplexer, you have multiple input, one single output, and the switch is trying to decide which one of the input connects to the output. With a demultiplexer, it's exactly the opposite. You have one single input, multiple outputs, and the question is, to which output should I connect this input? That's a demultiplexer. The meaning of include enable, the meaning of disabled output are exactly the same between those two. So are we doing okay so far with this picture? With what is a multiplexer and what is a demultiplexer? We okay? All right. So once again, in the lab, you probably want to go to the built-in help of Logisim. Let me bring that up to, and just kind of read about that, okay? It should be very consistent with what I just said in class. But just in case you're not writing down everything, or you missed something, the documentation is built in to Logisim. Are we good so far? All right. So the next item that I want to talk about is RAM. And we'll start with ROM, okay? We'll start with ROM first, and then we'll move to RAM. I'm gonna build another sub-circuit here. These are just experimentation circuits, so they're not actually that important. I call this RAM, but I will play with ROM first. So ROM belongs to memory, because after all, the name ROM means what? What do you think is the full name of ROM?
What is ROM? Read-only memory, exactly. So it is a kind of memory, except it's not supposed to change, okay? Now, inside the simulator, we can actually make changes by hand, but when it's in a circuit, it is for the most part read-only, which means the content is once the content is specified, you cannot change the content, okay?
So we can go ahead and give these things like certain values. So if you want to change the values inside a ROM component, there are two ways to do it. The quick and easy way is just to click on one location here and overtype it, okay? So if I want to change this location to 4E in hexadecimal, that's all you need to do. Click on that location, make sure the red rectangle is over that location, and then on the keyboard, just type over 2 digits in this case. So you'll be asking, why 2 digits? What? It's a ROM, so how many locations do we have in this ROM? That's the first question. It is a little misleading because what you see here, there are 4 times 4 or 16 locations, that's not all, okay? This is not all, this is simply a window into the memory of this device. You have to do a right click and then go to edit content. Then you will see a window that looks like this that allows you to change the content of any location. And this is the entirety of the memory of this particular device. So very quickly, let me show you how to read this memory content map first. The first column is not a content. The first column is the address of the first byte, the leftmost byte on each row. Let me say that one more time because I did use a lot of technical terms here. The first column is indicating the address of the leftmost location on each row. So that means where the mouse pointer is pointing to, that 00, is the address of location 00, which is the one that is highlighted, or there's a rectangle over that location. Okay, so once you're here, you can also change the location. For instance, if you want to change location 0, so it doesn't have the content of 00, you can just type over, okay? So let's just say I want to change that to F7. That's how I change it to F7. So the next question is, how do we know how many bits we can store at each location? And how do we know how many locations there are in the device? In other words, you can look at ROM as an initialized array, where you have control over how big of an integer is at each location and how many locations to be. Is that okay? So those 2 degrees of freedom are specified by address bit width and data bit width. So the question now is, so which one is which one? Address bit width, in many ways, is kind of like the number of bits for the select of a multiplexer or demultiplexer. In other words, in this case, because we have 8 bits to an address, how many locations do you think I can address, given that each address has 8 bits? In other words, we can go from 0, 0, 0, 0, 0, 0, 0, 0, 8 zeros, all the way up to 1, 1, 1, 1, 1, 1, 1, 1 in binary. So how many numbers are within that range, inclusive? That's the question. We got 8 bits. 256. 256, very good. So in this case, we have 256 locations. How wide is one location? That is controlled by data bit width. So data bit width controls what is the width of each location. In this case, they are both 8, but they do not have to be the same. Okay, 8 bits is also known as a byte, B-Y-T-E. So each location is a byte, and we can store 256 bytes within this ROM.
Any questions at this point? Questions? Okay.
All right, so I'm going to specify a few locations here. Okay, so I'm going to specify this is 6.3, and maybe just one more over here. This is 5.6. All right, so these are the locations, and you can see that the actual content updates at the same time. So now the question is, okay, now that we know that it can store some content, how do we get to the content? Okay, that's the next question. So we'll go ahead and specify an 8-bit input pin and connect it to the A port. Okay, the A port, A stands for address. So the address is basically what is inside the square brackets when you're using an array. I hope you all still remember what an array is from CISP310 and what a square bracket operator does to an array. So tell me again, what is the square bracket? What does it do, the square brackets?
Allows you to access a specific index.
Exactly. Go ahead, sorry. It let you specify the index, right, to index into an array so that you can specify which element in the array you want to access. The A port does exactly the same thing. Okay, it allows you to specify which location do we want to retrieve in this particular device. So that means your D port is the output, it is the value at that location. So let me connect an output pin here. It also has to be 8-bit wide in this case because each location has 8 bits. I just configure it this way by default. So this is it. Then you go like, does that make sense? This is specifying location 0, location is F7, and then in binary, it is outputting 1111, 0, 111. Does that make sense to you? Yes. Sorry?
I'm saying that it's outputting F7.
Yep, it is outputting F7. So if I want it to output 6.3, then I need to specify what address. This is a quick test to see if you guys can figure out how to specify the output or the D port to output 6.3 in hexadecimal or 0, 110, 00, 11 in binary. But how do we get that?
6.
So remember the 04 in gray is telling us the address of the leftmost byte on that row. This is 04, this is 05, this is 06. It's 06 in hexadecimal. So that means in terms of the input here, we have to change that to 0000, which is the 0, and then 0110 for the 6. Now we specify this location to be the output, and it turns out to be 0110, which is the 6, 0011, which is the 3. There's one extra pin here, which is the select pin. So let's go ahead and make use of it too. So the select pin really should be used because it is basically the same thing as an enable pin. In this case, you cannot hide the enable pin. A ROM always has an enable pin. Right now, the ROM component is not enabled because the select pin is a 0. And that's why the output are all X's here, which means, what do you think is the disabled output setting of a ROM? Even though you cannot configure it, what do you think it is? Floating, that's it, exactly. It is just not optional. You cannot select zeros, but it is floating. That's the only option for disabled output for ROM. But that means if I go back here and change the disable or change the enable pin or the select pin back to a 1, then it is once again enabled. And as a result, it is reflecting the D port is outputting the content of the location that is selected by the A port. Do you see a resemblance between this and the other 2 devices that we have talked about so far? It would be a good thing if you try to compare, because even though they are different devices, you can see the select pin here, okay? This is not the same thing as a select of a multiplexer or demultiplexer. It is more like the enable of a multiplexer or demultiplexer. The reason why it is confusing and it's called select is because the full name is chip select. It is whether this entire chip is enabled or not. Because on most circuits, there are multiple ROM chips, and you only want certain ROM chips to be outputting something at a time. So you need a chip select for each ROM chip in order to specify, okay, so we got 4 ROM chips here. Which one of you is supposed to give me the output? Oh, you right there. So I'm going to turn the chip select of you of this one single device to be a 1, but everybody else needs to have a chip select of 0. So that's why there's a confusion, because select really should be called chip select, not just select itself. All right, okay, so let's go to the A port, okay? So when you look at the A port, what does it actually resemble? What does it look like from the perspective of a multiplexer or demultiplexer? The select, exactly, okay? And in this case, it's not selecting from one of the inputs, it's not selecting one of the outputs, because ROM has its own content. So it doesn't need to select from a bunch of inputs, it doesn't need to select from a bunch of outputs, because it has its own content. So in this case, the A port is selecting which location in the ROM is being addressed. D port is the same as an output, okay? And there's only one of them, because you can only output the content of one location at a time. Are we doing okay so far with what a ROM component does? Okay. So are there any questions about, in real life, how do we get the content onto a read-only memory device? Because even though we are not supposed to change it, when we, as consumers, somebody has to put content into the ROM to begin with. Otherwise, there would be no content in ROM, and it wouldn't be a very useful device. So the question is, how do we put the initial content into a read-only memory device? So I'm leaving up to you guys to read up on that one, because there's a long history of different types of read-only devices. The original ones are called OTP, or one-time programmable ROM, which basically involves actual physically cutting circuitries to specify the content. So it really cannot change over time. And then later on, we have PROM, or programmable read-only memory device, or PROM. Those things are electrically programmable, but it's only one-time programmable, which is also by burning fuses, but it's burning those fuses on a special device. Okay, so you can purchase blank ROM devices and then have a special device to program those locations by quote-unquote burning the fuses. And then after PROM, we have EPROM. The E stands for erasable. So now we have erasable, programmable, read-only memory. It's going to make an English major, to have a migraine, because it's like, but it doesn't make sense. If it's read-only, how can it be programmable? If it's programmable, why is it also erasable, right? So the erasable part is using UV, ultraviolet. So you expose these things, it has a little transparent window. You expose it to UV light, including the sun. It will take a little bit longer when you expose it to the sun, but it will lose its content. It will lose its content in terms of memory. And then you plug that thing into a special device, then you can program the content again. It has a certain number of how many times you can reprogram it. And after that number of cycles, you have to throw it away. So if you guys are thinking, that has to be the worst one, right? It's erasable, programmable, read-only memory. No, that you can add another E to the whole thing. So you would be asking, what would be the other E? Electrically. So now we have electrically erasable, programmable, read-only memory, otherwise known as a double EEPROM. So in this case, you do not use ultraviolet to erase the content. It can be electrically erased. So you have to use usually a different voltage, or you have to use a different pattern. And that is the gateway to what you guys actually know and use, which is flash memory. So flash memory evolved from double EEPROM, and it's not exactly the same technology, but it's very similar. But it is different in the sense that when you want to erase a portion in flash, you don't need a special voltage. It is more or less it's controlled by the circuitry on the device itself, so you don't need to use a special external device to change the content in flash. So that's kind of a little bit of a history of these various types of read-only devices in quotes, because they're not exactly read-only, because if you can have something that's erasable and programmable, it's not exactly read-only anymore. All right, so after this, we can go to RAM. Okay, so let's go ahead and check out RAM as a circuit. Can someone tell me what RAM stands for? Random access memory. Very good. Okay, so you guys know your stuff. Very good. So we're going to pick out a RAM device here. So just by slapping the RAM device here, you guys go like, wait, hold on a second here. Tech, did you make a mistake and select another ROM device? Because guess what? They look really alike. Okay, there's the A port, there's the D port, there's the select pin. Those are in common. Okay, but what is different is this one also has a clock pin here. It has what we call a load pin, which specifies are we reading or are we writing. It also has a clear, because RAM, unlike ROM, is not read-only. You can change the content. Okay, I'm just checking the time to make sure that we have enough time to talk about all of this stuff here. All right, so what we'll do is we're going to kind of do the same thing, and we'll make a few memory cycles. We'll exercise a few memory cycles and see what we can do to change the content and access the content. And we are going to need quite a few of these single bit input pins, because we need ones for select, one for the clock, one for load, and one for clear. Go, and one more. All right. So the first thing is the trick that I showed you earlier. You can still inject content into RAM. In other words, if you want the RAM component to start with your specific content, you can do exactly the same trick that I did earlier. You can go to a location, click on it when you're using the poking tool, and then specify the content that you want to be injected into that location. For instance, if I want to change this to 9D, okay, this is all I need to do. Type it on the keyboard, 9D. If I want to change this one to 2.3, and then change this one to, I don't know, let's try F2. So that's how you can change the content in RAM using the user interface. Okay, so I'm not exercising the circuit at all to change these locations. I'm just doing it by hand right now. Okay, okay. So the next question is, I want to read certain locations. How do we read that 2.3 back? Okay, that's the next question. The first thing is you have to figure out the location of the 2.3. That's too easy. Let's try the F2. So if I want to output the content of F2 to the D pin, what do you think the address pin needs to do? What do you think it needs to specify? Remember, the leftmost column specifies the address of the leftmost location on the row. So that means this is 0C. Then we'll make this one 0D, right? 0D follows 0C. It's 0D. So if it's a D in hexadecimal, what does it look like in binary? So I'm just checking to see if you guys have it already memorized. Okay, first of all, what is D in decimal, in base 10? 13. So how do we express 13 in base 2 as a sum of powers of 2?
1101. 1101.
1101 in binary is correct. 1101 because it is 8 plus 4 plus 1. Okay, very good. So that means, we have to specify 1101 in the data pin, the address port here, 1101. The most significant 4 bits are zeros because, it starts with this particular 0 here. So every hexadecimal digit corresponds to 4 bits. So if you see a single 0 in hexadecimal, it corresponds to 4 zeros in base 2. All right, and you guys are going like, attack, nothing is happening. What's going on here? Oh, because I haven't selected the device yet, okay? But before we select, now you have to be careful because when you are dealing with a RAM device, you can also overwrite a location. So you don't want to overwrite when you're not intending to overwrite. So whether you are reading from the device or whether you're writing to the device is controlled by the LD pin. The LD pin stands for load, okay? LD is the abbreviation of LOAD, load. So when that pin is a 1, we are reading. When that pin is a 0, we are overwriting the content of RAM. In this case, since I'm trying to read, I really need to make sure that this pin has a 1 before I enable the device, because otherwise I can overwrite the content at the location that I have then specified. Okay, so what do you think I need to do next? Now that I have specified which location I'm going to read from, and this is a read operation, what do you think is the last thing I need to specify? Select, exactly. Once again, select is chip select, okay? It serves the same purpose as enable. So now I can click that one to a 1, and voila, okay? The output is now F2, because 1111 is an F, 0010 is a 2. So this is how we read, how we specify the location that we are reading from, and specify this as a read operation. Are we good so far with how to access RAM in terms of a read cycle? Great. So let's try a write cycle, okay? So let's go ahead and change this to a write cycle. The first thing I want to do is to deselect the component first when I'm making all the changes. So since I'm writing, I want the LD pin to be a 0, not a 1. And this time we have a little bit of a problem because the D pin is not an output anymore. So when you are overwriting the content of RAM, you are basically using the D pin as an input in order to specify, okay, fine, so what do you want to change this location to? It has to specify the new content. So that means I need another input pin now. So I'm going to specify another input pin, make it 8-bit wide, okay, because it has to correspond to the number of data bits, and hook it up to exactly the same port, okay? All right, so other than that, you guys would say, attack, which location do you want to change? Well, I don't want to make up all the decisions here. I'll let you guys decide which location do you want to change. It doesn't have to limit to what you see here because we know that we have 256 locations, which means we use 2 hexadecimal digits to specify the location. So you guys can tell me which location you want to change. Pick a number. 64. 64. Okay, so are you talking about 64 as in decimal, or 64 or 64 in hexadecimal?
Let's do it
As decimal? Okay. See, this is kind of like taking an order at a restaurant. It's like, okay, soup or salad, right? And if you choose salad, what salad dressing do you want? Thousand Island, or do you want a vinaigrette? Okay, you guys are not laughing.
For those people who are watching this, online or remotely, I'm pretty sure they are now, just walking over to the kitchen. Like, salad dressing, I want some. Okay, so you want 64 as base in base 10. So the first thing we need to do is to convert 64 in base 10 to hexadecimal, because that's the only thing we can do is in binary or / hexadecimal.
So what is 64 in hexadecimal? In other words, how many 16s do we use in 64? 4 of them, and it's even, okay? So that makes it very easy. 64 is 40 in hexadecimal. And once we get that, we can convert it into base 2. So what do you think 40 looks like in binary? Off by 1 bit. It's 0, 1, 0, 0, 0, 0, 0, 0. Okay, it's because we have
The 4. So we need to change the address to 0100 0000.
that would be 40 in hexadecimal or 64 in that's 64 in decimal. Okay, so we got that set up. And what content do you want that location to store now? Once again, super salad. 135. Okay, 135 in decimal. So how do we convert that into binary? Because now we need to specify
The new content in binary, 135, right? So that means we have at least one of the 128, okay? So then we have how much left? 7. So 7 is an easy one because 7 is 4 plus 2 plus 1. Okay, so now we have
the binary representation of 135. Okay, nothing is happening yet because I have to make sure all the other pins are configured correctly before I turn it on so that it starts to pay attention. The low pin is a 0. Yep, that's what we want, okay? Because if it's a 1, we are reading from that location. If it is a 0, we are overwriting that location. Okay, that's all good. All right, so I think we are ready to turn on the select pin, the chip select pin, which is
acting as an enable pin. So we turn it on.
okay. Well, the first thing is it is selecting the correct location, but it's not changing it. In fact, what is going on here? That's because RAM, like a register or like your edge sensitive D flip-flop, is edge sensitive. There's a clock. The clock is this little thing here. See this little triangle thing? That is symbolically showing us that is our clock pin. Once again, in this case, it's programmable or configurable, whether we want it to be sensitive to a rising edge or falling edge. By default, it is sensitive to a rising edge. So that means the clock pin, which is currently at a low state, we need to give it a rising edge by changing that pin to a 1. So we'll go ahead and do that.
And voila,
it just changes the location. So at this point, because it is edge sensitive, I can change whatever is presented to the D port all I want, but it won't change that location anymore because the update of the location in RAM is happening right at the instant when we change the clock pin from a 0 to a 1. Once we are at a state of 1, it is no longer going to change.
In other words, I can now play with these pins here and nothing happens to that location because it is now fixed. Is that okay? So I have just demonstrated a write cycle in terms of using RAM. All right, are we good so far? All right. Let me go ahead and take roll so that you guys have a little bit of time to absorb this. And I will do something. Okay, give me a second here because I need to move some windows around. When we are done with this, I'm going to show you something that's kind of interesting. All right, so you guys can keep watching this as I set up the roll taking activity. And if you have any questions, you can also, kind of jot down those questions. So when I'm done doing this part, I can come back and answer your question. All right, so we are now in the von Neumann architecture and memory. Go to the top, okay. Okay. All right, so if you go to the top of the module that we are on, which is the von Neumann module, you should find 2023-0321. Let me show you here. There we go. So this is your new rotating activity. The access code is EDGY, EDGY, which coincidentally is also the access code of the first lab activity for today. There are two, but it is the same as the first one. Yep.
Were we gonna get our tests back by the
It's all scored, but I have not made photocopies yet, so I cannot redistribute it back. So let me do some actual paperwork by destapling, putting those things through the scanner and then restapling it. Yep, that will take some time. Yep.
The quiz says I've done it already.
Yeah.
Oh, it's done already?
The thing from February 28th.
Yeah, it's the same as that one. So it's not using this title.
Using that title, but it's an old quiz that we've already marked through.
Oh, so
Yeah,
it
we
kept
can't
it. That's interesting. Okay. All right, well, that's all good then. Unless you missed the first one, then you can, you can participate with this one. Okay, well, that's fine. All good. All right, so let me show you the code of today's lab too, because that's also something that you need for today. Let me, I don't need this stuff in there. All right, so there are two labs for today. One is components of the processor, and then the other one is more processor components. So both of those are due tonight. This is the first one. The first one has the access code of EDGY, which is the same as what you saw earlier. This is the first one. And then the second one, I cannot remember what code I used. I'm gonna find it out right now. So for the second one, it does have an access, oh, shingles. I cannot remember why I used the word shingles on that particular day.
Really edgy. Well, shingles is painful, yes. So you can certainly do something like that. But today's lecture is not over yet, okay? I'm just making sure that you guys have the access code first. So what we'll do next, once we have introduced those components, so what we have introduced today would be registers, right? Because registers are basically just multi-bit, edge-sensitive, level-sensitive D-flip-flops, okay? We introduced the two types of switches. One is called a multiplexer, multiple input, one output. One is called the demultiplexer, which is the opposite, one input, multiple outputs. We have two memory devices, the read-only memory device, which is the ROM, we have random access memory, which is RAM. So those are the 5 devices that we introduced today. So the next question is, so how do they connect inside the processor, right? Because because I kept saying the processor is made out of those things. So let me switch back to Logisim, and then we can take a look at basically what you'll be using for the rest of this entire semester. That's just the help, which is not what I want. There we go. All right, so I have it already downloaded. You don't need it yet, okay? So don't worry if you do not know where to find it, because you don't need it yet. So let me go to Documents, and it's under Processor. Okay, there we go. All right, so this is the processor. I know it looks a little busy because it's actually zoomed in at 200%. So at 100%, it actually fits on one page. It's not really that bad. So you can see several things that you are familiar with already. This is the ROM. This is the RAM. This is a register. This is a multiplexer. And we got a few demultiplexers right here. DMX or demux is a demultiplexer. So this is basically what it is. This is what it looks like. There are a few things that are its own subcircuit. There is the register bank, which is its own component. Reg bank is its own component. But when you look inside, it looks like, I think we can recognize most of these things. We got multiplexers, we got a decoder, and then just a bunch of registers. So a decoder, I did not explain, because it's very easy to describe what it is. A decoder is the same thing as a demultiplexer, where the input is a constant 1. That's it. Okay, it's a single bit demultiplexer where the input is a constant 1. But other than that, it is the same thing as a demultiplexer. But it has a special name of a decoder. So this one is relatively easy. The more difficult component or the more complex component is the ALU, which is the arithmetic and logic unit. Once again, we find the multiplexers, we find the AND gates, OR gates, and then these are the things that actually do the computation. So I'm going to briefly describe those components that will do the actual computation. This is an adder, okay? So I hope you guys still remember when we talked about the carry look ahead adder thing. That's where it's going to sit inside the process. Okay, it is a very small component inside the ALU to do the actual computation. And then unlike the, this is a subtractor. So even though we did talk about how we can easily turn an adder into a subtractor by negating X first, as the P term and the G terms, in reality, in hardware, sometimes we implement these as 2 different devices. Okay, so in this case, there are 2 different devices. So the subtractor is used for subtraction, but it's also used for comparison. Because if you remember, we talked about the sign flag, the overflow flag, the L flag, and also the overall borrow flag. Those are all useful for comparison purposes. Okay, so those are all happening in the subtractor, mostly. This is a right shifter. Okay, a right shifter is, as the name implies, it basically just shifts the bits around in a byte. All it does, okay, is to shift in zeros from the left-hand side, move all the bits to the right-hand side, and whatever is already at the rightmost extreme of the byte, they're lost. Okay, that's what the right shifter is going to do. And then we have a multi-bit NOT gate, which otherwise to you is known as 1's complement. And then we have a multi-bit AND gate, as well as a multi-bit OR gate. And that's it. So this is actually the heart of the entire processor. All the actual processing, all the computation, they all happen here. And that's why it's called the ALU, the arithmetic and logic unit. Okay. And this particular circuitry over here, this one here, to be more specific, this is how overflow is computed. Okay, what it does is it takes the sign of the middle end, the sign of the subtrahend, and the sign of the difference. And it goes through the two AND gates here and the OR gate over here. I should be pointing this part here, not the top one, the bottom one. And it goes to the overflow flag. And then once we have the overflow flag, you can see also right here how we combine the sign flag and the overflow flag into the L flag using an exclusive OR. In other words, a lot of the stuff that we have learned in binary comparison, binary subtraction and whatnot, they are here again. Okay, so there are certain things from the past weeks that we will still be using in this semester. So that's why, when people ask, so are the tests, comprehensive or not? I say, I cannot really say for sure because it is implicitly comprehensive in certain cases. All right, so let's zoom back out into the main processor here. So I can tell you, generally speaking, what is important. The register bank is important because the register bank is really handy for providing values to the ALU. What do you want to add? What do you want to subtract? What do you want to compare? They must come from the registers. The ALU obviously is important because it does all the actual computation. But you only have 4 registers, okay? So imagine in a program, you only have 4 variables. And can you write a lot of programs using only 4 variables? Probably not, right? So that's why you also have RAM. So the RAM component, which is all the way out here, is basically the general purpose memory of the entire device, okay? There are 256 locations in RAM. So all the programs you'll be writing in this entire semester will have to fit in 256 bytes. And we are not only talking about instructions, we are also including the stack, the global variables, and so on. They all have to fit within 256 bytes. And in case you guys are wondering, what kind of useless programs can we write only using 256 bytes? Well, we can do binary search tree construction thereof, traversal. We can do Hanoi's tower. We can do Fibonacci, recursive way. We can do a lot of fun stuff, okay? With 256 locations, we can actually do a lot of useful stuff. So that's what we'll be doing until all the way to the end of the semester, is to write programs. So now the question is, so how do we get the content of a register to the ALU so it can do the computation? And when it's done, we want the result to be stored back into the register. And then when we run out of registers, we want to store things to RAM. So how do we get all of these things done? The answer are the multiplexers and the demultiplexers. Okay, if you think of this entire thing, okay, let me describe what entire thing means. Everything not counting this portion, okay, so this portion here and below is kind of special. So when you look at this upper portion here as the island of Sodor, then you're really just trying to specify which train goes from where to where at what time of the day. Now, if you guys do not understand what I'm talking about, the island of Sodor, let me show you what that means, okay? Because I think an image is really helpful in order to help you understand what we are dealing with here. All right, so let me maximize this screen. The island of Sodor. It is a fictional island coming from Thomas the Tank Engine. So you might ask, what is the big deal here? Well, there's a lot of train tracks here, right? The island of Sodor, Thomas the Tank Engine. It's all about trains, okay? There are multiple trains. So what do trains do? Why do we need trains? To transport stuff, right? So you can kind of imagine instead of transporting passengers or manufactured goods or minerals and whatnot, you're transporting bits, okay? Zeros and ones. And there are multiple places, like there's a junction right here,
There's a junction over here, there are junctions over here. So when there are multiple tracks combining to one single track, what do you find? Starts with S followed by W. Switches, okay, railroad switches. So this way you can say, at this time of the day, we switch to A. At this time of the day, we switch to B, so that different train can get into the switch and go out in different ways, or the opposite, okay? We allow different trains from multiple tracks to go out of that switch. So what is the job? What is the equivalent devices in the processor? The multiplexers and the demultiplexers, okay? So what about the stations, okay? What about, the stations where we pick up people? What about the stations where we drop off at a dock so the ships can start to ship things away? Memory devices, okay? What about the processing plant? We need this ore, we need this coal, and this is a steel plant, iron plant, to crank out your iron. So what about that thing? What do you think it is equivalent to in the processor? Which component of the processor says, okay, give me this, I'll do some processing, and I'll give you the end result? The ALU, okay. So that is why I use this picture, because now you get a kind of more physical sense of what the processor is really about. Okay, there are these train tracks, they're already fixed, okay? What is programmable are the switches. The trains are corresponding to who is supplying the content and who's consuming that information, that particular data, okay? So when you think of it that way, even though the processor looks really horrendously, complicated like this, but all it really does is to specify, hey, you can connect to that thing here because I have just laid down and controlled all the switches in between. Now there's a complete rail going from here to here. That's what it does. So the next question is, who gets to control the switches, right? Because it sounds like whoever controls the switches is controlling the operation of the entire island. So who is controlling the switches? I know we are sort of running out of time, but since we are on the roll here, I think it's kind of important to continue with this discussion here. So I'll give you this person, Sir Top Hat. You guys have to watch some of these episodes of Thomas the Tank Engine. This is also called the conductor. He is the guy in the control room that has switches on his desk. And they, in turn, changes the configuration of the railroad switches. Yes?
I'm just curious, if you go back to the circuit.
Yeah.
There's one line that was red. Do you know what that is?
Yes. So that line is red because the content is not available. So there's no actual content being output at the time. Oops. Okay, now just cycle through every single one. So you're talking about the flags out.
Yeah.
Yeah, so the flags out is red because it is unknown. The content is permanently unknown. Yeah. So that's the island of Solar. But the next question, the last, I promise this is the last question. So Topham has to do certain things. In other words, he is reading instructions from something else too. And this is the whole concept of a von Neumann machine or a von Neumann processor is, where do you think Sir Topham Hatt, the conductor, is getting his instructions from? The RAM, the programmer, you, okay? So you guys will be writing the assembly code that's going into RAM, and then Sir Topham Hatt is reading those RAM locations and go like, okay, so we need to produce iron today. All right, fine. Thomas, you go get some coal, and Henry, you go pick up some iron core, and then I'll do all the switches so all the trains can do their things, right? And then when how do you call places to produce steel? The mill, right? So the mill is done.
we want your Percy to transport the finished good to the dock. Okay, so that's kind of the story. So, when you have time, I really encourage you guys to watch at least one episode of your Thomas the Tank Engine, and preferably one that is narrated by the late, what's his name? George Carlin. Yes, because most people cannot imagine George Carlin doing children's show, and he did a terrific job at it. So there we go. I'll see you guys over at the lab.
Yes, we just mentioned recursion about like what you can do using these bytes. Do you know, do you have an opinion, like, is it better to use like recursion in the actual programming or just using the if statements and the loops?
Okay, hold on a second.